Hello, today we're going to talk about forces. So we're going to start out talking about what is a force. Well, a force is any influence that causes a body to accelerate. And most people have a pretty good intuitive sense of what a force is. It's really anything that you would call a push or a pull on a body. So it's going to be something that's going to cause some sort of motion. So each force is going to have three distinguishing characteristics. And this is kind of what we're going to model the rest of our talk around. First of all, a force is going to have a magnitude, similar to a strength. It's going to have a direction. And finally, it's going to have a point of application. So starting with magnitude, the magnitude can be thought of as the strength of the force. So, for example, if I've got this book, it takes some amount of force to lift up this encyclopedia of trees and shrubs. If you had a much larger weight, such as this giant weight here, you have to exert a much larger magnitude, a stronger force to lift that weight. And also, if that's the only force acting on an object, larger magnitude forces on similar objects tend to cause larger accelerations, the same object. So if I was pushing a car, I'd accelerate at a pretty modest rate. If this guy over here was pushing the car, he could probably get the car to accelerate a lot faster. So this is also where the units apply to forces. So anywhere we have the units, it's really the units for the magnitude of the force. So every unit of force is going to be some mass times some distance over time squared. And the mass is going to be the mass, and distance over time squared is an acceleration. So for example, in the metric system, we've got newtons. So 1 newton is a force that would cause 1 kilogram of weight to accelerate at a rate of 1 meter per second squared. And in the English system, our standard unit of force is going to be pounds. And that is going to cause 1 slug, that's the relatively unknown English unit of mass, which is about equal to 32.2 pounds, has a weight of 32.2 pounds at sea level. So it causes 1 slug, or roughly 32.2 pounds of weight, to accelerate at 1 foot per second squared. So moving on to direction, now we've got the magnitude. Forces also have a direction. So the direction is going to match the acceleration you would cause. So direction is important because, say I'm over here, I'm pushing on some car. If I have a friend helping me and he's pushing in the same direction, we're helping one another. If I'm pushing this way, my friend is pushing the other way, we're fighting one another. So direction is important in this. And with a magnitude and direction, forces are vectors. So when we work with them, we need to treat them as vectors, and we can't just treat them as numbers. We can't say, I'm pushing on this with 32.2 pounds, and this person is pushing on it with 60 pounds. Which direction does it go? Well, we need to know if we're helping one another, fighting one another, completely missing one another. So for example, the shopping cart, if I've got a pushing force, I'm pushing along the shopping cart, and I've got a weight force. These are perpendicular, so they're kind of independent actually. The weight of the cart is not what's fighting me, it's the friction of the wheels that's going to be fighting me. So, just as a side note with this as well, vector quantities, at least in these slides and in this book, are going to be represented with bold characters. So the pushing force, F push, this is bold down here, and F weight, that's also bold. That means that this is a vector, it has both a magnitude and a direction. We can't just treat it as a number in our equations. So finally, the third part of this is point of application. So every force is applied somewhere. And the big distinction we're going to make here is whether or not it's a single point of application or if it's being distributed over an area. So for example, we're going to first talk about point forces, which have a single point of application. So we're going to model this with a single vector. This would be something like if I'm pressing against the wall with a single finger, there's a little bit of area there, but for the most part I can kind of treat that as a single point force. Another example I have here, a bungee jumper. If we model the tension force in this cable, that would be something we would treat as a point force. The alternative to that is a distributed force. So a distributed force has more than one point of application. It's kind of distributed over an area or a volume, and they're modeled as fields of vectors. So the example for this, I could be pushing up against the wall with my entire back. I've got a kind of large area I'm exerting that force over. Or if I have something like a pile of sand here, this sand is going to be pushing down on the ground, and it's really got kind of an area that it's distributed over, and it's not even either. So I've got a field of vectors, and the force is less over on the sides, and towards the center, I actually have more weight pushing down on the ground. So this is the big difference that we need to pay attention to, because point forces we're going to treat much differently than distributed forces. It's kind of an extra step in analysis with distributed forces. So with that, we've got the magnitude, we've got the direction, we've got the point of application of the forces, and that's all we have for this video today. Thank you for watching, and I hope to see you again.